In this video, I'm going to show a relationship between work, kinetic energy, and potential energy. I'm first going to do that by showing that work is equal to a change in kinetic energy. Work is typically defined to be the dot product between a force vector with a displacement vector. So for example, suppose I was pulling a wagon. I might be applying a force vector in that direction, and it will have x and y components like that. But of course my displacement will be along the x-axis as I pull it forward, which means that work will be done in moving the wagon along the x-axis. Of course there will be no work done in the y-axis because even though there's a force component, there is no displacement. I'm not lifting the wagon off the ground. We can rewrite the above equation in integral form. Work is equal to the integral from a to b of the force vector dotted with an infinitesimal displacement vector. Next, we invoke Newton's second law, which says that F vector is equal to mass times an acceleration vector, which can be rewritten as mass times the time derivative of a velocity vector. Additionally, we can say that an infinitesimal displacement vector is equal to a velocity vector times an infinitesimal time increment. Rewriting the integral with these two in mind, we can write this as work is equal to the integral from a to b m the time derivative of velocity dotted with velocity times time infinitesimal time increment. Consider a some vector dotted with a, or a the norm of that vector. If I took the time derivative of a squared, it would equal, by the product rule, the time derivative of a dotted with a plus a dotted with the time derivative of a, which can be written as 2 times the time derivative of a dotted with a. So we can see that we could rewrite the time derivative of a dotted with a as 1/2 the time derivative of a norm squared. So we see that this is inside the integral, and we can turn that into this. So rewriting that integral from a to b m over 2 time derivative of v, length of v, dt, and of course pulling out the constants, we now have this. The next step would be to use part of the fundamental theorem of calculus, which says that the integral of a function f of x dx from a to b is equal to the antiderivative of that function at b minus f at a. And this tells us that we can write this as m over 2 V at B squared minus V at A squared. Vectors. Then, rewriting this in a more familiar way, I can say this is 1/2 m Vf squared minus 1/2 m V naught squared. So now we can see that work is equal to a change in kinetic energy. Next, to show the relationship between work and potential energy, I'm first going to write down the equation for kinetic energy. 1/2 mv squared. Next, I'm going to take the time derivative of kinetic energy. So this will equal dt of 1/2 mv squared will equal mv dv over dt. Now, if we're talking about potential energy, let's suppose we're talking about gravity, and in which case dv dt, which is an acceleration, if it's gravity, it's minus g. So we could write dk over dt is equal to minus mgv, which can be written as mg. Now velocity is, in terms of instantaneous, it would be a change in y with respect to time, because we're moving from A to B, however you get there. Gravity is a conservative vector field. It's irrotational, it's simply connected. So it's path independent. So it doesn't matter how you get from A to B. It matters that you got from A to B. Rewriting this equation to make it easier to see, I can write this as the time derivative of mgy. So we can see that the time derivative of kinetic energy is equal to the negative time derivative of some quantity. And if we integrate both sides with respect to time, we'd be able to see a change in kinetic energy is equal to the negative change in potential energy. Now, we already established that work is equal to a change in kinetic energy, and now we can see that it's also equal to a negative change in potential energy.